DeepWiSim, a wireless signal simulator for automated deep learning. DeepWiSim can automatically generate wireless simulation data and simultaneously train the deep learning model. It is built on Unreal Engine, which allows modeling realistic scenes with complex dynamics. In this system, we implement a real-time ray tracing engine for wireless propagation simulation and integrate the system with a deep learning framework for online model training. Also, we implement a UDP data communication layer for distributed deployment. DeepWiSim contains two main modules, a simulator and deep learning service. The simulator is responsible for environmental modeling. The real-time ray tracing engine simulates the signal propagation in the simulation environment. The measurement result will send to deep learning service in real time via UDP data communication layer. This UDP layer enables the remote distribution deployment by decoupling simulator and deep learning service. It allows the deep learning service to receive simulated sensor measurement and perform online model training. The trainer component is embedded with a popular machine learning frameworks and train the model with live measurement. Let's see the demo. Here, we create an indoor office environment and place a number of NPCs with animation for dynamic environment simulation. A sensor is attached to the right hand of our target, which simulates the human holding a smartphone. Now, let me start the game. There are a bunch of rays shoot from the sensor location. These rays bounce around the office to simulate wireless signal propagation with a real-time ray tracing engine. To see the measurement result, we can press M. This measurement will attach with a ground truth position of the sensor, then forward to deep learning service for online training. We can change the simulation parameter by press P. The setting menu allows us to control the target moving strategy, signal characteristic, and ray tracing engine. In idle mode, the target won't move as you see at the beginning. In constant mode, the target will walk with a fixed path. In random mode, the target will walk randomly around the office. At any time, you can press Tab to manually control the character, or press Tab again back to the observer mode. We can adjust the signal frequency and transmit power of wireless signal. The DPI controls the resolution of the sensor. This will affect the number of rays shoot from sensor location to simulate signal propagation. The trace distance controls the maximum distance a ray can trace. The trace depth controls the maximum number of bounces of each ray. Now, let's set the control mode to constant, which will let the character walk with a fixed path. To execute the deep learning service, we use Python command line interface. When we start the deep learning service, it will launch the trainer, preprocessor, and UDP client. The UDP client starts capturing measurement from the simulator. The preprocessor then stores live measurement in CSV format. When captured data reach the minimum size, the trainer will start to perform online learning. Here, we use a modified version of Deep AI model for the demo. Now, let's leave it run for a while. Here, we already trained the model for 50 echoes. Let's see the result. We use JupyterLab to visualize the result. The first result shows how loss change over time. The model converged very well in 50 echoes. At bottom of the evaluation file, we can see the prediction result of training data and test data. You can see both results align to the ground truth trajectory, which means our tool has successfully trained the Deep AI model for trajectory prediction. Thank you for watching.